Okay, well, I'm going to tell you a story because I'm working for NASA. I'm going to be telling you a story on behalf of NASA and the James Webb Space Telescope project, that telescope that was just mentioned that you see here in the first picture, and on behalf of all inhabitants of the Earth and all the future users of the telescope. So there's a long story, but now I'd like to move to the next slide, which takes us back several thousand years to Archimedes, who worked for the Defense Department of his day, inventing things to help protect the city of Syracuse from enemies that might exist. The drawings here are, of course, not contemporaneous with his work, but even in 200-something BC, he was already thinking about focusing light as a kind of a weapon that might be used against enemies. So in those days, he did not yet have a telescope, so we have to jump ahead 400 years ago to the next slide 3, which is Galileo's telescope of 1609. I think most of you know the story, that he did not invent the telescope, but he perfected it, taking a Dutch invention and increasing the magnification to 33 power. So with that small telescope, which you see one of them here, he was able to make maps of the surface of the moon and discover that it has mountains. He was also able to discover that there were satellites of Jupiter orbiting around it, that the planet Venus has a crescent as it orbits the sun, and even that the sun has spots. So we celebrated 400 years of astronomy in 2009, and now we have many more things to even think about since then. In my next slide, I would perhaps have a surprise for you. We astronomers believe that the atoms that we are made of have traveled very, very far through the universe, that they were not present in the early material, what we call the Big Bang, but are actually made in stars that have exploded. So those stars explode after completing the nuclear reactions that turn hydrogen and helium into the heavier elements that we see around us: carbon, oxygen, nitrogen, iron, phosphorus, calcium, all the things that the Earth is made of, were not present in the Big Bang material. In fact, the atoms have traveled many hundreds of millions of light years, many of them since they were liberated in those early explosions of stars. So this is a remarkable story that we are completely recycled material, and our atoms have traveled far and far away. So it is said that the stars died so that we could be here. So in the next chart, I want to begin to tell you how astronomers have learned these stories. So astronomers look back in time by looking at things that are far away. We see here an illustration of the speed of light. If you look at your hand, you see it about 1 meter away. It has taken about 3 nanoseconds for the light to reach your eye from your hand, which you would not easily notice. On the other hand, the sun, being 150 million kilometers away, sends out light, and we see it as it was about 500 seconds before we receive it. The nearest other star, it takes about 4 years for the light to get here. The center of our own galaxy, about 25,000 years for light to arrive. And if you could look back almost all the way back to the Big Bang, it would be almost 15 billion years, American billion, 1,000 million. So how do we know how far we're looking back in time? We have to know how far we're looking out in space. So in the next chart, number 6, I just illustrate the two main techniques that astronomers have. Thousands of years ago, ancient astronomers were already able to survey the universe, beginning with the surface of the Earth and the surveying methods. If you know one side of a triangle and 2 angles of a triangle, you know the entire shape of the triangle, and that's surveying. As it happens, the Greek astronomers were able to measure the size of the Earth and approximately the distance to the moon. They were not able to get the distance to the sun because the angles they needed to measure were too difficult for them to measure. Nowadays, we know the distance to the sun as well, and we use the fact that the Earth moves in its orbit around the sun every year so that we can draw triangles that include the nearest other stars. So this is how we measure distances to stars. The second method, which the Greek astronomers would also have understood quite well, is that if you have two things that you believe are identical in brightness, two candles, and one of them appears fainter than the other, you say it is because it is farther away. So this is called the inverse square law, and enables astronomers to measure the distances to everything as long as we can understand whether those candles are really identical. So that tells us distances, and of course, knowing the speed of light, we can tell how far back we are looking in time. In the next chart, I show you how we measure motions. Most objects do not move rapidly around the sky. We can barely detect their motion at all, even with telescopes, except for one thing. If an object is coming toward us or going away from us, the wavelengths of light that we receive are changed by the motion. So if you can spread out the light of the sun with a prism to make a beautiful spectrum or a rainbow, you will see that there are certain dark marks across the rainbow at certain wavelengths or colors. And those are due to the atoms and ions and molecules in the surface of the sun. If you look at a distant star and you see the same pattern, you say, then number one, that star is very much like the sun. You can also say, well, what if all the wavelengths are multiplied or divided by some number? And that would be due to the motion of the distant object. If an object is coming toward us, then we receive the waves from it more frequently, and the wavelengths appear to us to be shorter. If the object is going away from us, we see the opposite. The wavelengths are stretched out. So from these two techniques, we now have the ability to measure the chemical composition and physical properties of a distant star, and also to tell what is its speed of motion toward us or away from us. This is called the Doppler shift, and it has been known since the 19th century, and it's something that has a very similar effect on sound waves, which you can hear with your own ears when you're out driving in your car. So in the next chart, number 8, I want to illustrate the 4 great telescopes that were developed in the United States beginning in the late 19th century. A particular astronomer from Chicago came from a very prosperous family, and this was at a time when Chicago was the center of growth of industry and trade of the entire world. He had many rich friends, and he persuaded them to give him money to build new telescopes. So here they are. These are 4 great telescopes. The 40-inch or 1-meter telescope at Yerkes Observatory near Chicago, actually. Turns out to have not good weather there. It rains a lot. So he was soon convinced that he should go to California and build a telescope much larger than that. He built a reflecting telescope, the 60-inch, 1.5-meter telescope, and then the 100-inch, which is just over 2.4 meters, I guess, in diameter, in California on Mount Wilson. And those telescopes are still in operation today, as is his even larger telescope, the 200-inch or 5.4-meter telescope at Mount Palomar. So these telescopes were the basis of tremendous progress in the United States, and basically put the United States on the map of astronomy when it had been just beginning to catch up to European astronomers before that. So in the next chart, I have 3 pictures. You should see just the first one, I think, at first. The first image here is Erwin Schrödinger from 1927. He gave us the equations of quantum mechanics. And although many people are surprised by those, they are still the basis of every kind of modern technology that we use in electronics. The next image, I think you may have to push the button again. In the middle is Robert Goddard, who in 1926 gave us the first liquid-fueled rocket in the Western world, at any rate, and started the United States on its trajectory towards space travel. So, of course, the idea of the rocket was old. We've had firework rockets for many centuries before that. The third image that I show you here on the right-hand side is Albert Einstein meeting with Georges Lemaitre. As you know, Albert Einstein was the person who gave us 2 theories of relativity. The first one, called the special theory, in 1905, gave us E equals mc squared, one of the most famous equations of physics, and showed us that the speed of light was the maximum speed that anything could possibly go. So 1905, he showed us this, which was quite surprising. And it was based on, as we now interpret it, the fact that the speed of light is constant, regardless of whether the laboratory is moving. So his answer seems to be the only concise, simple answer to that observation that we made. So later on, of course, he gave us the general theory of relativity, just 100 years ago now. And the general theory says that because gravitation and inertia are proportional, that the action of gravitation can be described as a geometrical factor in which space itself is distorted by the presence of gravitating objects. He also concluded, by the way, at that time that gravitation has a speed, that gravitation moves at the speed of light. And that's just been recently reconfirmed by the discovery of a gravitational wave source where two black holes merged together in a huge burst of gravitational radiation. So George Lemaitre is shown here with him because in 1927, Lemaitre applied Einstein's equations of general relativity to conclude that the universe could not be static, as Einstein had believed, but must be expanding. So Lemaitre said the universe started with a thing that he called the primeval atom, which today we would perhaps call the Big Bang. At any rate, he knew that we would not know the laws of physics describing it, and of course he was right. He was not even the first. In 1922, Alexander Friedmann in Leningrad had computed the same equations, but Lemaitre did not know about those himself. So in the next chart, I show you two images again. The one on the left is Edwin Hubble, shown at the focus of a telescope in California. In the 1920s, the way you got a sharp image was to guide the telescope by watching a star and making sure that it stayed on the crosshairs and was aimed perfectly throughout a long exposure. The second image on the right shows you his first graph of the expanding universe. What it actually shows you is the distance of distant galaxies on the horizontal axis and the speed of motion on the vertical axis. The speed of motion, as you can see, is quite correlated with the distance. The farther away something is, the faster it is going, and it's going away from us. So now we look back at this and we say that this is Hubble's law, that the speed of motion is proportional to the distance, and that this is a measurement of the expansion of the universe. Now, to tell the complete truth, Edwin Hubble was never very sure that this meant the universe was expanding. He was looking for other alternative explanations. He was an observer. And even Einstein was not convinced yet by these measurements about the expanding universe. He needed mathematical proof, which eventually came from George Lemaitre, who showed that the static universe that Einstein had favored was not stable, was not possible to stay. So moving on to the next chart, I have again three pictures on this one. This is chart number 11. On the left-hand side, I have a picture of Lyman Spitzer. Lyman Spitzer was an astronomer who in 1946 wrote a report to the RAND Corporation, one of the American defense organizations, and he said, we should build telescopes in outer space because then we would be above the interference of the Earth's atmosphere and we would be able to get wonderfully sharp and detailed images of very distant things. He even imagined that if we could build a big enough telescope, then we would be able to observe planets orbiting around other stars. So, in the next picture in the middle, I have Sir Fred Hoyle. Many of you know that he was the person who gave the name of the Big Bang Theory to the expanding universe. I'm afraid that he's convinced so many people of this name that everyone has been confused, because the Big Bang is actually not a very good name for the infinite universe expanding into itself. The third image there on the right-hand side is me. I was born in 1946. Moving on to chart number 12, let me illustrate again some more people. On the left-hand image is Robert Herman and Ralph Alpher in the foreground, with an image of George Gamow behind. George Gamow was from the Ukraine, but he was working in the United States after World War II. And these two other men were young people working with him who started to develop up the details of what we now call the Big Bang Theory. They computed that the universe should have been very hot in the early times, that the heat radiation should still exist, and we should be able to measure it. They calculated the temperature that we should be able to measure, and they got 5 degrees above absolute zero, 5 degrees Kelvin, which is about right. The current measurement is 2.7. In the middle picture, I show you also that that people were hoping to see the canals on Mars in 1957, when Mars was very close by. Mars was very, very close. However, these canals that you see on the map were not there. It was a huge disappointment to the general public. And now we know, or at least we think we know, what those canals really were. Those canals were really the blood vessels in the back of the observer's eyes. And when they increased the magnification of their image of Mars enough, this is what they were getting. So the next big step in 1957, in the right-hand image, was a world-changing event in which the Soviet Union launched the first artificial space satellite and indeed demonstrated tremendous technical capability. The corresponding result in the United States was we have to invest huge amounts of effort in science and technology, and so we did. So NASA was formed only a year later. In the next image, I show you one of the large telescopes. This is the one in Britain near Manchester, which listened to the signals from that first Sputnik satellite, and has also done extraordinarily important work in astronomy, finding quasars, finding gravitational lenses, and even the case where a distant object is bent into a ring by the gravitational forces of the light on the light as it comes to us. In the next picture, number 14, I show you the antenna that was used to discover the cosmic microwave background radiation. In 1964, this antenna had been built to communicate with a Telstar communication satellite and also to do some astronomy. So two astronomers, Penzias and Wilson, were using the antenna, and they were very good engineers as well. What they found was that the receiver was producing extra noise that should not be there. And they were sufficiently careful that they proved that it was not coming from their equipment, which meant it had to be coming from the sky. They did not know that there was a prediction that this must be the cosmic microwave background radiation from the Big Bang. But now, of course, we know that it is. In fact, even when they had discovered it, they were not completely convinced that that was the real origin. It took many years before this was fully developed as a research project, and I will show you some of the other things that were done since. In the next picture, number 15, I have an image of a very, very large telescope we have here in the United States, in Greenbank, West Virginia. This telescope is a parabolic antenna that can be pointed in any direction, and it has got a diameter of 100 meters. Truly immense telescope. I have been there. I have on a day when you could walk right up to the edge of the dish, and it is astonishing how large it is. One of the purposes this telescope serves is to study pulsars. Pulsars are tiny stars, neutron stars, that have a mass even greater than the mass of the Sun, but are only 10 miles in diameter and can spin around hundreds of times per second. Those are extraordinarily interesting in their own right, but they also can be used for timing distant things with extraordinary precision. So this telescope can even be used in conjunction with the next one that I will show you to map the things in the solar system by radar methods. So this next chart, number 16, shows our very large telescope, about over 300 meters in size, in Puerto Rico, an island in the Caribbean area. This has a spherical antenna and a transmitter that can be moved around above it to point the telescope at different objects. This can both transmit and receive, and in cooperation with the telescope in Greenbank, it can send out radar pulses, which can then be received back from the surface of Venus, from the surface of Mercury, even from the surface of the satellite of Saturn called Titan, where we know that there are lakes of liquid methane floating on the surface. So an extraordinary set of radio telescopes that can be used to explore our universe. Now in the next chart, number 17, I show you the equipment that I worked on to extend the detection of the cosmic microwave background radiation. This is called the Cosmic Background Explorer, or COBE. It was launched in 1989 and operated for approximately 4 years to observe the cosmos. You'll see in the middle there is a collection of instruments protected by a protective shield, and it was put up to orbit around the Earth and observe the cosmic microwave radiation and to look for the cosmic infrared that might have come from the first generations of stars and galaxies. The observatory is still up there, but is no longer in use. So in the next chart, number 18, I show you our first scientific result. This is a measurement of the brightness of the cosmic microwave radiation versus the frequency, and measured in cycles per centimeter. So we found that all of the measurements fall exactly on the theoretically predicted curve, which has a special shape called the black body function. And so this is a direct confirmation that the expanding universe came from a hot initial condition that liberated and created this radiation field. So when I showed this chart to the Astronomical Society, we received a standing ovation because of the importance of the result and of the difficulty that people recognized from many previous experiments that had gotten wrong answers. So this meant that the Big Bang theory, the expanding universe theory, is actually probably right. One small caution: you can never prove something is right. You can, however, prove something is wrong. So in the next chart, I show you our second major scientific results. This is chart number 19. This is the cover of Physics Today magazine from June of 1992. And the chart to think about is the one at the lower right-hand corner. This oval map of the sky is actually a map of the entire sky compressed onto an oval. And it shows that the primeval radiation, the heat radiation of the early universe, is not equally bright in every direction. In fact, it is very, very slightly more bright and less bright in some directions. In this map, the pink regions are brighter by a few parts in 100,000, and the bluish regions, the blue-green ones, are cooler by about a part in 100,000. So when Stephen Hawking saw this map, he said that this was the most important scientific discovery of the century, if not of all time. When he said that, I thought, well, that's just very nice of him to say that. Now I understand that it's much more important than any of us really realized at the time, for multiple reasons. One is that we now believe that these spots are responsible for our existence. If these spots had not been there, the universe would not have been able to make galaxies, stars, planets, and people. We also know now that most of these spots are due to something called cosmic dark matter, which has gravity and enabled the galaxies to form sooner than they otherwise might have done because of the extra gravity. Astronomers are the only ones who can measure this dark matter so far, although we have hopes that people in ground-based laboratories will be able to measure the dark matter too sometime. So many reasons why Stephen Hawking would say that that was an important map. Eventually, we hope that we will have a theory of the universe that includes quantum gravity and might explain exactly why these spots are arranged the way that they are. In the next chart, chart number 20, I illustrate that the universe does not have to have a center. Many people, when they hear the name Big Bang, imagine actually a small bang, a firecracker, which occurs at a place and a time. In our case, the expanding universe appears to be infinite in extent and to have no center and no edge. So this illustrates only that astronomers measuring each other's positions and velocity in outer space would have a hard time telling who was in the middle. When we calculate from Hubble's law, we say we can imagine what it would be like to be an astronomer living on another galaxy. And we conclude that every astronomer on every galaxy would think that he or she was at the center of the universe. The conclusion is there is not a center. There is no center. So in my next chart, I illustrate that I cannot draw you a picture. You cannot stand outside the universe to draw a picture of the universe. There is no other place to go. So just as a reminder, the Big Bang should be replaced by the expanding universe as a description of the early times. So in my next chart, number 22, I show you a little bit about how the early universe made us. Gravitation is a very powerful force reaching across huge distances of space and is able to stop the expansion of material by pulling back on the expansion. It means that the gravitation can cause the galaxies and the stars to form, providing there's enough gravity. So this is what enables stars to form, and then after the stars form, of course, then they can make the nuclear reactions in their interiors that produce the chemical elements of life. So we are here because gravity is a long-range and attractive force. In my next chart, I show you one of the great observatories that has been built for studying our origins. This is called the ALMA, the Atacama Large Millimeter Array, and this is an electronic telescope in the mountains in South America at an altitude of over 5,000 meters. The telescope operates by having a computer compare the signals that are coming in from all of these different antennas and make an image that represents what the sky must be to produce all of those electronic signals. So the image in the upper left shows you a new star, which is in the process of forming planets. So the image illustrates dust grains orbiting around that new star and sending out heat in our direction that can be picked up with the telescope. As it happens, this is exactly what astronomers thought should be happening, but had never been able to observe directly before. What we see here is the dust is organized into rings, just as the dust grains orbiting around Saturn are organized into rings. And we see that there are dark regions in between the rings where we imagine that new planets are being born today. The next chart, number 24, I show you pictures of a new telescope that is being constructed now called the Square Kilometer Array. Can you imagine a telescope covering an entire square kilometer? It's done electronically again, and it's being built in two parts, one in Western Australia and one in South Africa. These telescopes are put in places where nobody lives and nobody has a cell phone, which makes it possible for us to do this work. It is calculated that this telescope is so powerful that if there's a civilization on a planet orbiting a nearby star that has airports and radars like ours, we would be able to pick up the radar signals from those distant planets. So what can we do besides radio? In the next chart, number 25, I illustrate something called adaptive optics. As soon as telescopes were possible and were large, people realized that we could not get very sharp images because the atmosphere of the Earth is turbulent and is always shimmering and dancing and make the distant images of stars blurry. So back in the 1950s, it was imagined that if we could correct for that dancing atmosphere with an adaptive optical system that would correct for the motions of the atmosphere, we could get sharp images. So that's been finally developed. It was first invented for military purposes, then it was reinvented decades later for astronomers to use, and now we even have it in use for eye doctors. If you go to the eye doctor and you say, "I don't see very well," the doctor can look through the lens of your eye to get a much better picture using this same mathematical method. And if you're very determined, then of course the eye doctor can improve your eyesight using laser surgery to be much, much better than what we are all born with. So we will use this in the next telescopes that I'm illustrating here in chart number 26. These are 3 gigantic telescopes that are being built today, much larger than the biggest ones that we have now. One will be 24 meters in aperture in Chile. It's called the Giant Magellan Telescope. We'll have 7 circular mirrors operating together. One will be the European Extremely Large Telescope, about 40 meters in diameter, also in Chile. And finally, an American project called the 30-meter telescope is going in Hawaii, on top of a mountain there. So all of these telescopes are in progress, and all of them will use this adaptive optics method that I just illustrated so that they can get sharper images. On the other hand, none of them are powerful enough to answer every question. And so I'll show you a little bit about space telescopes now and where we hope to go next. Chart 27 shows you the Hubble Space Telescope. Hubble is 25 years old, almost 26, will be next month, and is working beautifully. So as you know, it is above the Earth's atmosphere, and it takes sharp pictures that are better than almost anything we can get from the ground, even though it's a small telescope compared with what we can build on the ground. It's working well because it's been repaired 5 times and upgraded by astronauts in their space suits going up on the space shuttle. Now the space shuttle does not fly anymore, and so that was the last time that we know of for the Hubble to get upgraded. But it's still working beautifully and will be operated for many years to come, we hope. In the next chart after that, I have one of the pictures taken by the Hubble. This is called the Hubble Ultra Deep Field, and astronomers decided that they would point the telescope at a direction where there was nothing to see, where there were no galaxies and no stars that they knew of. And what we saw after pointing the telescope in that one direction for 2 weeks were thousands and thousands of galaxies and a very small number of stars, and a big surprise. The telescope showed us that the galaxies, like the Milky Way, were formed much, much earlier in the expanding universe than people had imagined when the Hubble was designed. And they are formed so quickly and so early in time that, that we know that the first galaxies cannot even be seen with this Hubble Space Telescope. The picture shows you many beautiful yellow galaxies, blue galaxies, some little red dots, but the expansion of the universe stretches out the light from the most distant galaxies so that a wavelength is too long for the Hubble to detect it. Closer to home, chart number 29 shows you the Whirlpool Nebula, and this is typical of many galaxies orbiting around the common center, hundreds of billions of stars held together by gravity. And this one illustrates that different colors show you different things happening in that galaxy. The dark regions, the brown regions, are due to dust grains absorbing the starlight. The blue areas are stars where are new stars that have just been born, and the red areas are where stars are being born today. So this is a way of us learning about our history by looking at the history of other galaxies. In chart 30, I illustrate what I told you at the very beginning, that stars blow up and liberate the chemical elements of life. This is one that did so in AD 1054, as seen by astronomers here. We know actually the very day on which it occurred because although it was seen worldwide by everyone, astronomers in China wrote it down, and we still have records from those days almost 1,000 years ago. So this star is typical of stars that blow up and are called supernovae. In the next chart, I illustrate that we have learned something very surprising about the expansion of the universe. For most of time since the expanding universe was first recognized in 1929, astronomers believed that surely the expansion is slowing down because the gravitational force of galaxies pulling back on each other must surely slow the expansion. But we should go measure. So In the next chart, I show you 3 people who measured and discovered that it's not true. The current universe is accelerating. It is going faster and faster every year. These 3 men shared the Nobel Prize in 2011 for discovering the acceleration, which we now call by the name of dark energy. However, to be completely truthful, we do not know what the dark energy is or if it even should be called energy at all. All we are entitled to say is we know the universe is accelerating. So now I want to wrap up by talking about the James Webb Space Telescope, which is my current project. The James Webb Space Telescope is an international project being built by NASA and the European and Canadian space agencies. And the place where I work at Goddard Space Flight Center is the lead organization for it. So we are building this telescope, which you see in the right-hand corner of this chart, number 33. We see here a large hexagonal mirror, which is about 6.5 meters in diameter, which will collect distant star light and galaxy light and focus it into the instrument package. The telescope is protected by a set of 5 thin plastic membranes coated with metal, so that the sunshine cannot reach the telescope, and the telescope will always be in the dark and will be very cold. The purpose of this is so that the telescope can pick up infrared light that comes from the most distant universe and also from objects that are not warm enough to emit visible light. So the telescope will be cooled down to about 45 degrees Kelvin, 45 degrees above absolute zero, just by being placed in the dark behind this big sun shield, this big umbrella. It is planned for launch in 2018 in October on a European rocket called the Ariane 5, and it will be carried out in approximately 1.5 million kilometers into space. We are carrying fuel to operate the observatory for 10 years. So in the next chart, I illustrate, on chart number 34, where we are sending the telescope. There are a set of 5 Lagrange points, which are places where the combined gravitational force of the Sun and the Earth is enough to pull the observatory around the Sun once a year. So we choose the one called L2, which is just a little bit farther from the Sun than we are, and then, so the observatory can stay near there all year long. It was actually discovered in 1750 by Leonhard Euler, but he only found the first 3 points. Lagrange found the other 2 in 1772. So in this chart, number 35, I want to show you our telescope and how it will unfold in space. So if it plays properly for you, you should see now a telescope unfolding in space. First, we unfold the solar panels. Then we unfold a small parabolic antenna to communicate with the observatory. Then we begin to unfold the sun shield. This is all done by remote control. No astronauts are there to help. We separate the telescope from the spacecraft so it can be cooler. We unroll the covers from the sun shield. Now we eventually pull apart the sun shield until it's all stretched out and is as large as a tennis court. And we'll finally separate the 5 layers of the sun shield. This is all done by pulling on cables with motors. And the last step is to unfold the telescope itself. It finally will look like a telescope. This very difficult mechanical design is necessary in order to get the telescope as large as it takes to observe these most distant objects. So in the next chart, chart number 36, just illustrate the fact that we will be testing our telescope in a gigantic vacuum tank here on Earth to make sure that it will focus when it is cold. As almost everyone knows, the Hubble Space Telescope was not in focus when it was launched and it needed to be repaired. We do not have that opportunity with the Webb telescope, so we have to test it completely here on the ground and make sure that there's no problem with it. So the vacuum tank is about 20 meters in diameter and almost 40 meters long. So it's big enough to put the whole telescope in and verify focus. Now on this chart, chart number 37, I have a movie of the early universe according to the theory of gravitation operating across space and time, as I told you. This is a supercomputer simulation that shows the effect of gravity on the dark matter and the ordinary matter. In the computer, they've been able to stand back and pretend that the universe is not expanding, so we can follow the motions of just a small volume. They've also managed to rotate this small volume in front of our eyes so that we can see the three-dimensional structure growing. So you see that the gravitational forces are able to pull galaxies together and to put them in strands and even organize them in almost flat sheets like you see, something that was not really expected from theoretical reasoning alone. You also see now that some regions are having gigantic explosions. These explosions can occur from two major energy sources. One is the stars themselves that explode, and one occurs when a black hole can occur, and material falling into the black hole can release huge amounts of energy as well. As the universe continues to expand, the gravitation continues to stop the material from expanding, pulling it back in. And when the universe is about 9 billion years old, things quiet down a lot. Most of the explosions come to an end. And roughly at that same time, the solar system forms from the debris of all these other explosions. It's a beautiful movie, and we'd like to know whether this movie is a true movie. So the only way to know is to go take pictures with a telescope to see if the pictures match the ideas that are shown and implemented in the supercomputer simulation. Of course, even when we do take our pictures, we cannot watch the movie of the universe. We need the computer to help us imagine how the universe would change through time. So going on to chart number 38, I show you just an example of one of the things we'll be looking at with the telescope. This is a place called the Eagle Nebula. It was observed by the Hubble Space Telescope, and it's a place where stars have just been born. Beautiful bright stars and glowing gas clouds and huge columns of dusty material that prevent you from seeing the stars as they are being born. If you look at the next slide, slide number 39, here's a picture of the same place as observed with infrared telescope on the ground in Chile, and you can see that the dust no longer prevents us from seeing inside the cloud, and this is a place where we will be looking to find out how stars are born. The next chart, number 40, illustrates the possibility that we can find planets are orbiting other stars by watching the stars and seeing them blink. The first movie, the one on the left, shows what happens when a planet goes in front of its star and it blocks some of the starlight. We have thousands and thousands of candidates of this kind of event observed by the Kepler Observatory. Sometimes when the planet goes behind the star, we can also see that, as is shown in the movie on the right-hand side. This only works if the planet is very bright, but sometimes they are. In both cases, we can now learn directly a great deal about the planet, not only how large it is, but how warm it is, and even can understand the chemical processes in the atmosphere of such a planet by looking for the details of the light that it absorbs from the star. So with some luck, we have the hope of finding a planet that's like Earth and measuring whether it has enough water vapor to have an ocean under that atmosphere. Chart number 41 illustrates that we have ambitions for even larger telescopes. If we could build a telescope 12 meters in size or more, then we would have the ability to see those little Earth-like planets out there, even if they're not passing directly in front of their star, and even examine them to see if they have oxygen. Oxygen would be a clue that such planets are alive, because here on Earth we have oxygen because of plants and algae in the ocean. This is something that astronomers are wishing for. We have not yet decided to build one, but I think it's possible. So within our lifetimes, within a few decades, we could know if there are planets out there with oxygen that are alive. So I'd like to conclude with a speculation on chart number 42 about how far humans can go. I think that we can see that we have robots going everywhere on the Earth. They're drilling holes in the bottom of the ocean to get oil. We use them for digging tunnels. We send them to Mars. We send them to Pluto. We send them everywhere. And so robots are getting more and more capable. And they do not mind if it's cold or dark or vacuum. They do not have to breathe. Human beings can go to Mars, and of course many people want us to go. NASA and other people around the world are working on plans to do that, but it's difficult and dangerous. So even though there's a movie called The Martian, which is a wonderful movie, nevertheless, this is going to be a difficult trip. On the other hand, in the distant future, I think the robots are going to get smart as well as capable, and we will be asking them to take us on a long trip. So let me conclude here with a slide number 43 that says there is more information available on the internet. There is a website for the James Webb Space Telescope. There is a cosmology website called lambda.gsfc.nasa.gov. The Nobel Prize Foundation has a lovely website where all the scientists all explain what they've done. And there's even a small paperback book that I wrote some years back to summarize the story of all of these things. So if you would like, we have some time for more questions. I'd be happy to interact with you on things that may be on your minds. Thanks very much for coming for the talk.